Okay, here's my second intro to thermal chemistry video. So this is a follow-up. It's going to be a short video just on some basic math and basic concepts. So from the last video, we know that because the energy of the universe is constant, we know that the change in energy for our system plus the change in energy for our surroundings equals 0. Therefore, the change in energy of the system is equal to the negative change in the energy of the surroundings. So what that negative sign means is that it's an opposite process. So if the energy of our system was a positive number, the energy of the surroundings will be a negative number. But because the energy is constant, the quantity associated with this, the number, is going to be equal, just the sign is going to be opposite. So from this, we have the relationship between the enthalpy change in our system is going to be equal but opposite to the change in energy in our surroundings. Okay, and just to refresh, if our enthalpy change is positive, then the system is endothermic. Meaning it absorbed energy from the surroundings. So energy is absorbed from the surroundings, so Q would be negative, meaning delta T is negative, meaning TF is lower than Ti, than the initial temperature. So basically, the surroundings got colder. And they will feel cold. The temperature went down. If delta H is negative, then the system is exothermic. Energy is released to the surroundings. So Q will be positive because delta T is positive, meaning T final is higher than T initial. So the temperature of your system, of your surroundings, the temperature of your surroundings went up. So your surroundings feel warmer or even hotter. Okay, some example calculations using the surroundings formula, Q equals MC delta T. Now, you use this formula anytime that you take a temperature of something. Whatever you take a temperature of, that substance is your surroundings. All right. So Mrs. WP has been drinking a lot of tea lately. How much heat is required? So we're looking for Q. to heat 300 milliliters of water from 22.0 degrees Celsius to, let's make that 100 decimal, T final, 100 degrees Celsius. I'm going to stick in a decimal there, so that has 3 significant digits. Q is equal to MC delta T. We need mass of our surroundings for this question, but I'm given the volume of the surroundings. So you actually have to convert and show your conversion if you want full marks of your volume to your mass using the density of that liquid. For water, there's 1 gram for every 1 milliliter, and you're going to assume that any conversion factor has an infinite number of significant figures or significant digits, so it will not affect your rounding in your final answer. So this gives us 300 grams of water. So now we're going to plug that in. 300 grams times 4.19 joule gram degrees Celsius times 100 degrees Celsius minus 22 degrees Celsius. Be careful here. Don't get sloppy. Don't drop your significant digits. Don't drop your zeros, because you'll end up typing into your calculator what you wrote down, and then you introduce rounding errors to your answer. So this the answer to this is 98,046 joules. Now, we often convert all of our joules to kilojoules. There's 1,000 joules in a kilojoule. Again, this is a conversion factor, so an infinite number of significant digits. So this is 98.046 kilojoules. To round off to the proper significant digits, look at your initial data. 22.0 is 3 sig figs, 100 decimal is 3 sig figs, 300 milliliters has 4 sig figs. So our final answer is limited to 3, because that's the smallest number there. So 98.0 kilojoules of energy is required to heat 300 milliliters of water from 22 degrees Celsius to 100 degrees Celsius. Okay, what is the final temperature? So we're looking for TF. If 50 grams, so that's our mass of water, is heated from 25, so that's our initial temperature, using 5.15 kilojoules of energy. So that's our Q. So I want to find TF. So Q is equal to MC delta T. You can solve for delta T by rearranging. So Q divided by MC, because you move the M and the C to the other side, you do the opposite math. They were multiplying, now they're dividing. And you can solve for that, and then once you have that answer, you can substitute in TI to solve for T final. Isolate T final by moving the initial temperature to the other side of the equation, or you can substitute directly into your, you can, depends how comfortable you are doing algebra, set this up to solve for initial temperature right away. So move M and C over to the other side, and now TF will be equal to Q over MC plus TI. You'll get the same answer no matter which way you do it. I'm going to assume that you can do it the second way if you choose. I'm going to show it the first way using the 2 steps. Okay. C units are joules, gram, degrees Celsius. So you have to make sure that the Q, the mass, and the temperature are all in those same units. So our Q is currently in kilojoules, so you have to change that to joules first. Again, you should always show your work rather than plopping numbers in. What I end up usually doing is just whatever the value was, sticking a times 10 to the 3. That's supposed to be a 3. Yeah. Joules. Okay. So 5.15 times 10 to the 3 joules. I'm going to work from, I've rearranged that equation, over 50 grams times 4.19 joule gram degrees Celsius is equal to my delta T. So 5.15 times 10 to the 3 joules divided by, oh shoot, sorry, 209.5 joule per degree Celsius. I'm going to show you this calculation step by step. I'm going to try not to skip any steps because I know there's different levels of math strengths in the class. Okay, so delta T is equal to, if I take 5.15 times 10 to the 3 joules divided by 209.5 joule per degrees Celsius, because these grams canceled, then I get 24.582 degrees Celsius. Okay, so second part. Delta T is equal to TF minus T initial. So T final is going to be equal to delta T plus TI. I just moved the T initial to the other side. So plug in my numbers, 24.582 plus 25.0, all degrees Celsius, equals 49.582 degrees Celsius. I'm adding these two numbers, so I can only round my answer to the 10th decimal place, because this is the least accurate number. So 49.6 degrees Celsius was my final temperature. So when I heated the 50 grams of water from 25 degrees Celsius using 5.15 kilojoules of energy, the final temperature that it rose to was 49.6 degrees Celsius.